In the 1850s, human ambition hit a hard physical limit. The world ran on cast iron, a metal that was cheap but dangerously brittle. Steel, the infinitely stronger alternative, was a luxury reserved for small hand tools and watch springs. This material vulnerability became violently apparent during the Crimean War. British artillery units discovered that their standard iron cannons couldn't handle the explosive pressure of heavier, grooved projectiles. The guns were literally bursting apart, sending jagged shrapnel back into their own ranks. Enter Henry Bessemer. He wasn't a veteran ironmaster, but a serial inventor who had previously dabbled in everything from movable date stamps to gold paint. He proposed a radical machine that he claimed could mass-produce cheap, high-quality steel in minutes. Bessemer was proposing a process that could do in 20 minutes what traditionally took days of manual stirring and melting. If his mathematics held, he was about to replace artisanal forging with industrial-scale chemistry. Bessemer unveiled his machine in 1856 with a triumphant demonstration. He effectively dropped the cost of steel production from 40 pounds per ton to just 6 or 7 pounds. Thrilled by the massive profit margins, British ironmasters eagerly bought up licenses to build the machine themselves. Then the rollout began. The ironmasters set up their own converters, poured in the molten metal, and waited for steel. Instead, what poured out was a crumbly, highly brittle mess. It was completely useless for manufacturing. The backlash was absolute. The press and the iron industry turned on him instantly, publishing scathing letters that publicly condemned his machine as the most audacious fraud since the South Sea bubble. Yet, Bessemer hadn't faked his demonstration. His prototype really had produced perfect steel. The industry was left with a bizarre forensic mystery. Why did the exact same machine work flawlessly in Bessemer's workshop, but fail catastrophically the moment it was built anywhere else? To understand the failure, we have to look inside the converter. The blueprint relies on a highly counterintuitive idea, pushing high-pressure air up through the bottom of a vat filled with molten pig iron. Pumping cold air into liquid metal sounds like a great way to cool it down, but the oxygen in the blast acts as a catalyst. It binds with impurities like carbon, silicon, and manganese, triggering an exothermic reaction. The iron actually gets significantly hotter as the impurities burn away into gas and slag. After about 20 minutes, a bright blue flame shoots out from the mouth of the converter. That specific color is the chemical signature of burning carbon monoxide. When the flame dies down, it means the carbon is entirely gone. But there were no digital thermometers in the 1850s. Veteran steel workers had to rely entirely on physical instinct. They operated the air valves by feeling the rising heat radiating off the converter's outer wall, stopping the reaction at the precise second before the iron itself began to oxidize. On paper, the physics and chemistry of the machine were a flawless triumph of engineering. The problem was geology. This chart shows the elemental breakdown of different iron ores. Notice the massive spike in phosphorus for the standard British and European ores. Bessemer had unknowingly tested his prototype using imported Swedish ore. By sheer luck, he had selected a raw material that naturally contained near zero levels of phosphorus, bypassing the issue entirely during his demonstrations. When the British ironmasters ran their own local phosphorus-heavy ore through the converter, they hit a fatal design flaw. The inside of Bessemer's machine was lined with a silicious clay, a material that is chemically acidic. Because an acidic lining cannot react with or neutralize phosphorus, the element was left untouched by the violent air blast. This microscopic poison remained trapped inside the metal matrix, turning the final cooled steel impossibly brittle. Bessemer hadn't committed a malicious crime. He had simply built an idealized machine that couldn't handle the chemically messy, unpredictable reality of the natural world. The converter remained largely impractical for European ore until a young clerk and amateur chemist named Sidney Gilchrist Thomas identified the chemical mismatch. He proposed a solution: replace the acidic clay with a chemically basic material like burnt limestone. This swap changes the environment inside the converter. The new lining reacts dynamically, pulling phosphorus out of the molten iron and trapping it in the solid slag. With the lining corrected, the converter could finally process everyday, cheap iron ore into the high-quality, pure steel required for structural engineering. To finish the process, workers added a carefully measured cocktail of ferromanganese and aluminum. This removed any trapped nitrogen bubbles from the blast and dialed in the exact carbon content required for maximum strength. With the chemistry finely balanced, production scaled up overnight. Steel manufacturing transitioned from a slow, painstaking craft measured in days to an industrial behemoth producing 30 tons of metal in 40 minutes. The immediate impact was felt beneath the feet of the public. Brittle cast iron rails, which had a habit of cracking under heavy loads, were replaced by steel rails that lasted 10 times longer. This abundance of cheap, durable steel allowed for the rapid expansion of railroads, physically linking continents and accelerating global trade. The success of the process came from reconciling a lab-proven theory with the chemical impurities of the natural world. It proved that a patent is only as valuable as its ability to survive the messy reality of the Earth's crust.